Hello everyone. In this video and the next video, we are going to talk about specific terminologies, specific, I would say, calculations, formulas, and so on that you will need and you will see a lot in machine learning. Now, for many of them, I'll try to just briefly pass over them because each one of them might need a lecture of their own. And the focus here is not to cover those prerequisite material, but just to refresh your mind if you haven't heard about them, if you have heard about them and you work with them, but your knowledge might be a little bit rusty, or if you haven't at all, at least this one will trigger you to go and learn about those topics a little bit more. So let's get it started. The first thing that you need to work with a lot is feature, right? So feature is basically any individual measurable property, any thing that you can measure and you use it in your inputs, your outputs, and so on to basically quantify the machine learning problem, right? Because, for example, let's say here the goal is to identify an image, right, in another image, or let's say the goal is to find interesting objects in it, or recognize text, or anything like that. So, what are some of the features that you might be able to use? So one of the common features that you see, for example, in images are corner points. If you look, corner points are one of the common features. Where are they located? What are their positions with respect to each other, and so on? And how would you describe the vicinity of the corner point? And in my other playlist on computer vision, one of my future lectures will be allocated to detecting corner points using the Harris corner detector. So this is one. Another one that you can see a lot in many of the computer vision machine learning algorithms are edges. Edges, right? The boundaries that the light intensity changes dramatically from one region to another are some common features that you see in images for recognition and higher level tasks. But there are other types of features that have been introduced into the body of machine learning during the last 2 decades or 3 decades, maybe 2 decades or so. I would say 3. And some of these features are not as easily describable compared to the edges and the corners. Like, for example, one of them is called surf features. So these features are the areas in the image that basically the point or the small region and the surrounding of it, that describing them and recognizing them not only in this image, in any other deformed version of this image, they are easy to recognize. Okay, so SURF stands for speeded up robust features. So one of the most important thing for many of the features that you use in whether computer vision or machine learning is that these features are robust. And robust means if something happens, let's say for example here to that image, like the image is rotated, it is scaled up, it is shifted, it is cropped, right? It is deformed, there is noise added to it or anything, you are still able to detect those features and describe their vicinity. Okay, so they are robust, and we call them also invariant. They are invariant with respect to, let's say, rotation or scaling or translation or something. So anything that we can use and we can form a vector with those measurable entities, we can call it a feature. And so the input to your machine learning algorithm could be a bunch of these features, right? So your input vector could be, for example, here are like the edges, right? Here are the corners. Here are, for example, the light intensities, and so on and so forth. Or if it's like economy system, a finance system, then there are other things, right? The inflation in the markets, right? The interest rate, the for example, some histories of that organization, and so many other factors. I'm not expert on it. So you form what we call a feature vector, and you can use it as the vector for input, for output, and so on and so forth, right? Okay, so this is what we have as a feature. Input is clear. Those feeding things to your machine learning, and outputs, or the labeled entries, are the correct classes, the correct outputs for those inputs. So if I pass this to my machine learning algorithm, I expect it to send back to me the class of bananas. So the correct class, the correct data, the correct value associated for any input, we call it the target or the desired output. And we say these data are labeled, right? Like these, if we are talking about classification. Now, we need to go to the scaling and measuring distances. So before I go to scaling, I would like to first talk about distances, and then I go back to scaling. One of the major things in any machine learning algorithm is measuring distances between two vectors. So let's say here, this vector that I specified, now I have one vector called x, and I have another vector called y. Now I want to know whether these two vectors are close to each other, which basically means whether these two vectors represent the same class or same type of data or not. So I have to measure the distance or the similarity or the closeness, any of them that you want to say, between x and y. How would you do it? There is not a single measure of distance in machine learning. The most common one that we use a lot, and everybody knows, is called the L2 or Euclidean Norm, which basically you subtract each and every one of the elements of x and y, square the result, add them together, and take the square root, right? But that's not the only one. One of the other ones is called L1 or Manhattan Norm. Manhattan Norm or L1 norm is what? Instead of taking the square root of all of these differences, you take the absolute value and sum it up. And why we call it Manhattan, you can go look it up. I don't want to spend a lot of time, but basically this is another way you give to this norm is called taxi cab. So if you ever hear the word taxi cab, the word taxi cab means also similar to when you are driving basically a taxi. And of course, whoever named it, they liked Manhattan in New York. So this is like going from block to block, and this is the number of blocks that you go pass in either horizontal direction or vertical direction. So this is like you're driving in a city, and from here all you can do is to go either left or right or go up and down. You cannot go diagonally. So if you want to go from here to here, then let's say you have to go 2 horizontal blocks and maybe 3 vertical blocks. So if you add all of these individual ones together, that is similar to this Manhattan norm. Then we have the Chebyshev, or you might also call L infinity norm. Here, instead of taking all of these individual absolute values and add them together, all you do, you look at the maximum of them. And the maximum absolute value of differences between x and y, that is called the L infinity norm. You also have what? You also have the cosine of the angle between two vectors. Okay, where you dot product two vectors, divide them by the product of the magnitude. This is like the cosine of the angle between them. Okay. And then we also have what we call the Maholabanous distance, a distance introduced by a scientist in 1936, which basically shows the distance between a point and a distribution. So this time the distance is not between one point x and another point y. This is between point x or p and a distribution of points. And how would you show the distribution? You show it with the average value in that distribution, mu, and with the covariance matrix, S. Okay, so if you subtract S from mu, transpose it, multiply by inverse of the covariance matrix, multiply by x minus mu, take the square root of that. This is called the Maholabanous distance. What is this? It basically shows you how many standard deviations point P is away from mu. Right? It's a multi-dimensional version of that. And we're going to talk about it in a second when we go to this scaling. We're going to talk about more about how many standard deviations you are away from the center. But this is another distance that we hear a lot in machine learning, Maholabanous distance, when your goal is to find the distance between a point and a distribution. Okay, so I can go and solve examples for each one of these, but again, the goal is just to give you basically a push, if you haven't heard about any of them, to go and study more. Okay, I'm not going to cover each one of these topics in details with examples. So now going back with all this, going back to the scaling. What is a scaling? Well, now when you compare two vectors x and y and you want to find the distance, the notion of distance is meaningful if and only if the scale of x and y are what? Are similar. If they are of different scales, then taking the distance using any of these formulas is meaningless. What do I mean by that? Let me show you. So let's say I have vector x. This vector x is like, for example, let's say 0.9 and 0.1. I have vector y, which is like 1 and maybe 0. And I have another vector, maybe a. And this a vector is, let's say, for example, like 10 and 0. So now the question is this: is a closer to y or x closer to y? Right? So I want to find distance of x and y, and I want to find distance of a and y, and see which one is what? Bigger. Right? Well, of course, just looking at the numbers, you can definitely say x and y are closer. So it means x and y should belong to the same class, not a and y. Of course, because these numbers are less than 1 and 1, this number is 10. Right? But if you look, if you scale y by a factor of 10, you see that's exactly a. So maybe a is the same class as y, really, right? Or it's closer to y compared to x, but for some reason it was magnified during the process. So a, in a sense, might be way closer to y compared to x, because look, the entries are replicate of the other one except for a scaling factor. Right? X and y are on the same scale. A is another order of magnitude bigger. So maybe this comparison here is meaningless. Unless I come and say, hey, this class is a class with class magnitude 1. This is magnitude 10. So I somehow come and divide this by a magnitude 10 and say now the A new or A modified, whatever you want to call it, is now 1 and 0. Now guess what? Which one is closer? A prime is closer to y than x. So whenever you want to compare data in machine learning, it's always a good idea to make sure they are on the same scaling. Unless you have a reason not to do it, they typically try to make them the same scale. How? One of the common ways they do it is if you have a distribution of data, let's say X, Y, whatever, all of them, you subtract each data from the average of all data and then divide it by the standard deviation, and then you get a what we call normalized or Gaussian normalized version of X. What does it have to do with Gaussian? Well, if you look at the Gaussian distribution, if I want to compare two distributions of data here, right? How do I compare two distributions? For example, here, again, similar to comparing these data, if I want to say, is the yellow distribution closer to, let's say, the blue, or the red is closer to blue, or the green is closer to blue? How can I tell? Well, it's not so easy, especially about the green one, because the center of the green one is different from the center of the others. There is a shift here. So the first thing I would do is I subtract the average of the green from it. This top operation alone will bring the center from mu, if it was mu, the center of X. When you subtract mu, now the center comes at 0. And then when I divide by sigma, I change the spread, right? I divide by the spread, so now instead of the sigma being any arbitrary number like this, now my sigma is what? My sigma is going to be about 1. Okay? So basically, this one, if X was belonging to a normal distribution with mu of mu and sigma of sigma, or sigma squared, now this X, sorry, the original X. If the original X coming from a normal distribution with arbitrary mu and sigma, now this new X is coming from a normal distribution with average of 0 and standard deviation of 1. Okay, that's why we call it normalized. So now I can compare these different distributions, because now their centers are at the same and their spreads are normalized. So this distance now that I calculate is scale independent and shift independent. Okay, so just keep that in mind. Okay. Now let's jump onto something quite a bit different. It's called curse of dimensionality. What is it? So we hear in machine learning a lot that as the dimension of the feature space goes up, the problems of clustering and classification, especially clustering, becomes harder and less meaningful. Okay? So as, again, the dimension of feature space, which means the number of features, goes up, then clustering problems become meaningless. Well, what does that mean? Well, consider here the dimension of the feature space, or the number of features here, is 2. I have one axis here and one axis here, right? I have 2 features. Let's say F1 and F2, or U and V, or whatever you might call it. Now, if I have a bunch of circles here on some corner of this square region, and I have some triangles data on another, Well, clustering is quite meaningful, right? Because I can say, well, these two data form one cluster and these two data form another cluster, right? Now, if I add one more to the number of features, so here I have what? On this cube, the number of features is equal to 3. I have a u-axis, I have a v-axis, and I have a w-axis. Now, what I can have is these two circles do not need to be on the top of each other or next to each other. One of them could be on this corner, one of them could be on the other corner. When I look at it in the W direction, it looks very similar to this. Similarly, if I look at the triangles, one of them could be this corner, one of them could be this corner. So now, how many clusters do I have? Should I say 4 clusters? Well, then how many data belongs to each cluster? Guess what? Only 1. Right? So now each data can be isolated in a corner of this cube, or in general, hypercube. And when each data has a cluster of its own, then clustering doesn't mean anything, because clustering means more than a data. It means several data become one group. That's clustering, right? If it's each data can find a corner of the cube and go and stay there, and then call each one of them a cluster, then it's completely meaningless. So as the number of feature goes up, there is a better chance that each one of your data can go into one corner or be in one corner of this hypercube and become a cluster of its own. Okay, and why would that happen? Because as long as you look at U and V, these two circles are very similar in terms of magnitudes of U and V. But when another factor comes in like W, now you're increasing the chance that for W, the two circles have a different value. Or if you add another one, then for that factor, these two circles will be separated. Okay, so that's called curse of dimensionality. The higher the dimension of the feature space, the harder it is to do clustering, and the more it can become meaningless. Okay, so just wanted to clarify this curse of dimensionality. And before I move to the next topic, maximum likelihood, I just remembered that I wanted to clarify this Maholabanous distance that I mentioned, right? Which I said it is like how many standard deviations you are away from the mean. You can see it's exactly related to this scaling, right? Here, the result of this, if this number, let's say this modified x is 3, here, if I say this x is 3, what does that 3 mean? It means your original x was what? Was mu plus 3 sigma. So it means the data was 3 standard deviations away from the mean, right? If this modified version of it is 3. If it's 5, means 5 standard deviation away from the mean, and so on. Which also, as you get away from the mean in a normal distribution, the probability of that data goes down. So that's why you see it's exactly related to what? The Maholabanous distance. But instead of this being a 1D transformation, this one is what? A multi-dimensional transformation. Just wanted to clarify that for you before I open up the new topic. Okay, now what is the maximum likelihood estimation and model parameters or hyperparameters? So this is based on the idea that I have a system, a model, and from this system's model, there can be so many observations that are obtained or acquired, right? I have a system with a model, and this model has some parameters like W. Correct? The system also has some input and some observations or outputs. If I call the output or the observation of the system X, so observed data, if I call it X, and if I call the parameters of the system W, The goal is, if I don't know the W, I don't know what W is, but I will get some observations from the system, some X's. How could you give me the W's, the parameters of the system model, so that it maximizes the chance that these observations are actually taken from that model? Like what? Let's clarify it with an example. Let's say I have a system and the model of the system is a normal distribution with an average of mu and a variance of sigma squared, right? Now, from this model, I don't know what mu is, I don't know what sigma square is. I just know the system has a normal distribution with these two parameters that I don't know. From this distribution of the outputs, I'm going to take a bunch of samples. I'm going to take a bunch of observations, x1, x2, and xn. The question is, could you tell me what was the mu, what was the variance or sigma squared of the model, just based on what? Just based on a limited number of observations, right? How can I do that? To clarify it better for you, I use a MATLAB example. So let's say here, you know, in MATLAB there are several commands that can generate random numbers. One of them is rand, one of them is rand n. There is rand I. Of course, you have to pass to it inputs. You cannot just say rand I. You have to say basically what is the maximum data and so on, and how many data you want. So you have to say rand I of, let's say, 8 and 1 and 1. Then you can get something, right? But what I want to focus on is rand n, which gives me random numbers drawn from a normal distribution. This rand gives me random data from a uniform distribution. And this one are integer random numbers. So if I use rand n, data taken from a normal distribution, what is the sigma and what is the mu that this command is using? Well, I can just look at the help of MATLAB and it tells me, but if I don't know, what I want to do is this: call this command a bunch of times, and each time it gives me a different random number. Look at that. So if I get a bunch of these observations, bunch of these outputs, and I look at them, can I estimate what is the mu, what is the sigma or sigma squared of that normal distribution from which these numbers are coming? Can I do that? That's this problem of maximum likelihood. I want to find mu and sigma which maximizes the likelihood that these data are coming from it. How do I do that? Well, if I want to do it on the paper first, what do I do? So I say, well, the chance that the data x comes from a distribution normal with mu and sigma squared, the model of it is what? As you know, the formula for a normal distribution, 1 over square root 2 pi sigma squared, exponential of negative x minus mu squared divided by 2 sigma squared, right? Good. Now here, let's assume that drawing any of these samples from the distribution or generation of any of these outputs has nothing to do with the other ones. In other words, these data are what? Independent from each other. In the rest of this video, at some point, I'll talk about conditional probabilities and independence. But it means the chance of drawing x1 has nothing to do with x2 or xn or anything, right? So if these these outputs are all independent from each other, then the chance that I can get all of these outputs from the same normal distribution is going to be the product of the individual ones. So if I could get x1, like plug in x1 here, and it gives me the formula for it. If I plug in x2, it gives me x2. If I want to get all of them at the same time, it means what? Or together, it should be the product, and that's where we use the pi term. Pi means product. So we multiply the individual ones, and that gives me what? This constant term, which is in all of them, it's going to be raised to the power n because I have n of them. And all of these exponentials, the denominator of them is constant. Their numerators are going to be added together. That's why we have the sigma term. Correct? So now what do I have here? This formula is the probability, the model of all of these data, x1 to xn, coming out of that normal distribution. Now what? Now I want to make sure this function is maximized. I have the maximum chance for such happening because this term here is a probability, right? This is the formula for a Gaussian distribution probability. So this term is a probability, and I want to maximize this probability. How? Because this term here, this guy, is a function of what? Mu and sigma. So if I change mu, if I change sigma, given all the xi's, which are given numbers, I can change this function, right? Let's just focus on mu alone. So if I call this, whatever you want to call it, J maybe, right? That's what we called it. For the rest of the notes, I call it J of mu and sigma squared. This J is a function of mu and sigma squared, given all the x's, right? So if I just focus on mu, let's say, this function, and I plot J versus mu, it can have what? It can have some value here, some value here, some value here, some value there, up, down, and so on and so forth. And I want this point, the mu for which what? This function is at the highest chance, correct? Of course, the function also depends on the xi's. So what do? I use my calculus knowledge. I take the derivative of this function, partial derivative with respect to mu, set it equal to 0. If I do that, I can easily find mu, and mu that I find based on the maximum likelihood, we call it mu maximum likelihood. The mu that I found by maximum likelihood method is simply gonna be the average of the data. Just add all of these xi's divided by the number, and that is going to be what? The average of the data. So the best estimate for what? For the average of the population, the best estimate for the average of the population is what? The average of the sample. And if I take the derivative with respect to the variance or the standard deviation, set it to 0, then the variance or the standard deviation squared based on the maximum likelihood is going to be what? Is going to be the variance of the sample. So it says if your data are coming from a normal distribution, if you want to know something about the what? The whole population, the best way is to find those estimates directly from your sample. Right? Let's say if I want to know the height of the people in a country, right? The male height, let's say, for example, to make it more specific, how do I do that? Can I go and find every single male person and take their heights and then find a distribution like this and then look at where the sigma is, where the mu is? No, it's impossible to get all of the data. All I can do is to just get a sample of the data. And if I get this sample and this sample is a bunch of independent data, then I can just look at the average of my sample and the variance of my sample and say those are a good representative of what? Average of the population and the variance of the population. And this is what the maximum likelihood could do for you if your data is normal. If it's not normal, if it's another function, still you need to find this function which is the likelihood function of all data, right? The joint probability, we call it. The joint probability that all of these data are drawn from that model with those parameters, and then set the derivatives of this function to 0 with respect to the parameters, and from those from the equations you can find what? The parameters or hyperparameters. This is called the maximum likelihood. Now going back to the MATLAB example, so to automate this, because I need a bunch of data, I write a very simple code, and in here I say, let's say I start vector A as empty, and then I say for, or let's call it X if you like, for II equal 1 to n, generate the random data, and then what? Pass it to this vector X. I mean, augment it. That's one way. The better way, if I don't want to do all these for loops, is simply I say what? X equal rand n of n and 1. That's as simple as that. You don't need to write a for loop, because this built-in function in MATLAB does generate as many as you want. Just you tell me how many data you want. Let's say 1,000 data points. So it is going to get 1,000 data from the normal distribution with unknown mu and sigma, and call it X. And then I say, give me the mean of X, and give me what? The STD of X, the standard deviation. That's all I want. Let's run. Call it test. Typo, but that's okay. And look at the data. It says the average is negative 0.05 and the standard deviation is 0.9798, something like that. Now, if I do a little bit more data, look. The average is very close to 0, 0.006, and the standard deviation is almost close to 1. And those are the exact numbers. If you look into the help, mu for rand n is 0 and sigma is 1. Very similar to this guy that we talked about, right? The normalized standard, the normalized Gaussian function, mu of 0 and sigma of 1. That's what the rand n command is. And the more and more observations you make from the system, it makes your maximum likelihood estimates to be what? To be, let's call it mu. Mu ml, right? And then sigma ml. It makes your estimate much closer to what? To your actual numbers. Seems like I did write something in the wrong place. Here we go. Okay. So you can call them mu maximum likelihood and sigma maximum likelihood. Okay, as simple as that. So hopefully it just gave you a spark. If you haven't seen this topic, you go and look at it, because we are going to deal with this topic a lot in machine learning. So please go ahead and take a look at that. And let me here emphasize one more small thing before I go to the next topic. And here, if you see, instead of me directly taking derivative from this function, since it's an exponential function that involves mu and sigma, what I did was I took natural log of this function, which converts it into a linear function of mu and sigma now. And that makes, when you calculate this partial derivative with respect to mu, it makes the derivation a lot simpler. Now you might say, well, you changed the function. Instead of this function, now you're looking at natural log of the function. Does it change the optimal points? No, it doesn't. Why? Because the function natural log of x, if you look at it, it is a monotonically increasing function, correct? the natural log when x goes to 0 goes to negative infinity. When x goes to positive infinity, it also goes to positive infinity. Correct? So it is a monotonically increasing function like this. And so if you apply it on f, then the optimum point of f and the natural log of f are the same. And this is a very common practice. Many times before you do the derivatives, you transform the function with some monotonically increasing or decreasing function, especially increasing because you don't want to change the location, and then you take the derivative to make the derivations and finding the optimal points simpler. Okay, so now let's move on to the confusion matrix. True and false, positive and negative definites. What are these? So many times when you have a classification algorithm, you want to know how good your classification algorithm is doing. So let's say if I go back to this initial picture, I have trained a model, a machine learning system to, if I give it a picture of what? Of some fruit, it can tell me what kind of fruit it is, right? Now I want to test how good my system is doing. So this is what I will do. Here I'm talking about a binary classification. So it is not multi-class like the picture that you saw that I have 3 types of fruits. Here I assume 2 types. Let's say what? Let's say it's either banana or it is not banana. Okay, then what's going to happen? So here, I formed this matrix. I formed this 2 by 2 matrix where I pass to it a bunch of pictures. How many? Let's say for this figure here, 165 pictures I pass to it. And I know, because I have a human who is checking these pictures, how many of them are actually bananas, how many of them are not bananas. So I know out of these 165, 105 pictures I gave to my algorithm were actually bananas, and 60 of them were no bananas. Okay? Now, how did my algorithm do? My algorithm turned out and find out that 110 images were bananas and 55 were not bananas. So it predicted no or predicted yes, while the actual no and yes were quite a bit different numbers. So clearly you see it had detected 5 more pictures as banana than reality and 5 less as not being banana. It did detect 5 less than the 60. So now how good is my algorithm if I want to quantify the performance of the system? One of the things, the simplest thing is to come up with 4 categories: true positive, true negative, false positive, and false negative. And what are these? True positive means what? Means it was actually a banana, and my algorithm could detect a banana. So it did the right job for a positive or yes case in this case, right? True positive. So it was a positive case and I did the job correctly, so it was true. Or what? It was negative. It wasn't a banana, and my algorithm also said no, it's not. So it was a negative case, and again I did the true job. I did the right. So you see these 2 diagonal elements where the prediction and the actual data are matching, we call them true because my algorithm did the job. And the other cases where my algorithm did opposite to the reality, it was here what? What was here? It was, you say, false positive. Means I said it is positive, but it was false. It was not right because it wasn't. It's a false positive. It's a wrong yes detection. And here I have false negative. I said no, it is not, but it was. Because these two are contradicting each other, the result is false. So anti-diagonal elements of this matrix are what? Are false data. Because prediction and reality don't match. Okay? Now let's say in this case, it says my true positives were 100. What does that mean? Remember, I had 105 real banana pictures. I detected 110, but because I detected 110, does it mean my algorithm detected all of the correct 105? No. Out of that 105, only 100 detected were bananas. So what does it mean about the rest of it? 10 of that were falsely detected as bananas. They were no bananas, they were apples or peaches detected. So again, pay attention. Because my detected ones were more than actual ones, it doesn't mean I detected all of the actual ones. I only detected a portion of them. The rest of them I could not detect. Where are those fives that I didn't detect? It's here. Right? These fives were bananas, but my algorithm says no, although they were bananas. So you see clearly that what? That sum of these two numbers, 5 plus 100 is what? 105. And similarly, if I look at my no actuals, plus 50 and 10 is going to be what? It's going to be 60. Similarly, if I look in the column, 10 plus 100 is what? 110, and 50 plus 5 is what? 55. Okay? And then whether I add 60 and 105 or I add 50 and 110, the result of that is going to be what? Is going to be the total 165. So this is called a confusion matrix: true positive, true negative, false positive, and false negative. Of course, my algorithm has done a great job if what? If the diagonal elements are very, very large and the off diagonals are what? Are very, very small numbers. Ideally, if these two are 0 and those two, sum of them make the total, that's perfect accuracy, right? If it's a diagonal matrix, if this matrix is a diagonal, sum n1 here, n2 there, and 0 and 0, that's perfect accuracy and everything. But in reality, I would never get, most of the time, some perfect prediction. So now we can quantify the error a little bit better than just looking at the magnitudes of these numbers. We look at some ratios. So that's where we create some what? Rates or ratios here to quantify better the performance of the machine learning algorithm. And that's where these ratios or rates come into play. Okay, one of these rates is called the accuracy rate, which is the total number of correct predictions, which is true positive plus true negative, divided by the total. And 1 minus that is, of course, the error rate. So this is the simplest method for finding the accuracy. So in here, I have 150 out of 165 that I could detect correctly. So this one times 100% is my accuracy rate, right? Or 1 minus that in percent is error rate. There are a few other rates that you might hear in the literature, so I want to clarify them for you. One of them is called precision rate. The precision rate is the true positive over true positive plus false positive, which is what? Here, divided by the total of these. So it's, for this case, it's going to be 100 over 110. So it says out of the positive cases, means out of the cases that you predicted yes, how many of them were actually yes? So if detected positive, what is the chance that it was actually positive, right? So let me write that for you here. If detected positive, what is the probability of being positive? It's interesting that this text does move with, there we go. Here, right? That's the meaning of the precision rate. Then we also have some other rates like the recall, which is also called true positive rate. It's the number of true positives over true positives plus false negatives. So you basically, instead of dividing true positive to the whole column, you drew the true positive to the whole row, right? Like this. What's the meaning of that? That means if the actual thing was yes, right? What is the probability that you predicted yes? So it's kind of opposite of that. You see here it says if detected positive, what was the probability of being positive? Well, recall is, if I want to give it a meaning, I have to say if it was positive, what's the probability of being detected as positive? We also have specificity, okay, specified or true negative rate, which is 1 minus false positive divided by true negative over false plus false positive, which again, if we go back and look at the confusion matrix, false positive, which is here, divided by false positive plus true negative, which is here, and 1 minus that, which is basically, you can say, true negative over the whole row. So it's really this guy, right? Because it's 1 minus that, so it is going to be like true negative over true negative plus false positive. Which means what? Which means if it was not, if it was no, then what is the chance of being detected as no? And finally, we have prevalence, which is true positive plus false negative over total. And here, if you look, your true positive and false negative are here. And over total, which is basically the ratio of actual positives over the total. So it has really nothing to do with your predictions, okay? You have to say the ratio of positives over the total sample, or the prevalence of the positives, basically. Okay, so the meaning of these terms hopefully is clear to you. Now, some might say, well, although the confusion matrix and those true and false positive negatives are good and these rates are amazing, but which one of them, if I want to come down to one single number for comparing the performance of one machine learning algorithm against another one, which one of them? Because maybe one method shows a better precision rate, but maybe a smaller recall rate or something like that. Could you combine all these different ratios and numbers into one single measure that we can use for comparison? And the answer is yes. It's called, one of the methods of combining is called Matthews correlation coefficient, which, by the way, is very much related to, or you can say it's the same as, for binary variables instead of general distributions, you can say it is the same as what we call Pearson correlation coefficient, and it was first time proposed by Pearson, not really Matthews, but in the literature. It is, in machine learning especially, they call it Matthews correlation coefficient, or MCC. And this MCC is a way of combining all of these true, positive, negative, false, and all of the four numbers in the confusion matrix. You combine them based on this formula that you can see here. And the good thing is the result of this is always going to be between -1 to 1. Where 1 means the method prediction was perfect. 0 means the method did not do better than, you just toss a coin. Basically had no real prediction power to it. It was completely random prediction. And 50-50, like, and -1 means the method prediction completely were in disagreement with the actual result. So whatever the actual was, if it was positive, the method said negative. If it was negative, the method said positive. Okay, so basically if you looked at the confusion matrix was completely anti-diagonal. So the diagonals were like 0, and the anti-diagonals, some of them form the total number of samples. That's like -1. So this is one way to do it, and as I said, it is related to the Pearson correlation coefficient, which for two variables x and y, which come from two distributions with averages of mu and standard deviations of sigma, you can find this correlation coefficient rho of x and y by expected value of x minus mu x times y minus mu y divided by sigma y, and again this number is between -1 to 1 with the same meaning for -1, 1, and 0 that we had for Matthews. Okay, so that one is a derivative of this guy for a binary class where the values of x and y could only be 0 or 1, yes or no, positive or negative. In general, x and y could have a lot more values than just two binary values, and that's where, if you want to use this generalized version of this, use this guy, Pearson correlation coefficient. So actually I covered both of the topics for you here. The next topic is called the covariance matrix. What is that? So if I have just two random variables x and y with so many entries, let's say n entries, then the covariance, which is the amount of variation of two variables together, how much two things change together, if I want to calculate that, sigma squared of x and y, then I can subtract each x data from the average of x, subtract each y data from average of y, multiply together, and then sum it over all of the entries and divide it by the number of entries, or entries minus 1, if I want to remove the bias. What is bias? What does removing bias has to do? That's a separate topic of its own. We'll get to it at some point, or hopefully I will cover that under my probabilities playlist. But this is showing how these two can, and you can write it in a vector format too. X, write it X as a vector minus X, and then dot product by Y minus Y bar divided by the number of elements. Now, covariance matrix is very similar to this, but it has not just one entry, one number like this. It has, for X and Y, it has 4 entries. So the first one is sigma squared of X and X, which is what we call the variance, right? If X and Y are the same, then it's going to be variance of X. If they are both Y, it's variance of Y, and if it's XY or YX, the order doesn't matter. So this element is what? That's the covariance value between X and Y. So this matrix is definitely always what? This matrix is symmetric, because the order of X and Y in this formula does not affect anything, right? So the diagonal elements of the covariance matrix of variance of each one of the vectors, and the off-diagonal elements are the covariance between 2 of the components. So now if you have, in addition to X and Y, you also have a Z, this is going to be a 3 by what? It is going to be a 3 by 3 matrix, right? So here you will have sigma squared of, let's say, X and X, then X and Y, then X and Z. Right, and then here is going to be Y and X, which is the same as X and Y and Y, and Y and Z, and similarly ZX, ZY, and ZZ. Right, so you see the variances, and you just need half of this. The other half is similar. The other triangle is similar. So covariances and variances. That's called the covariance matrix of the data. That your data includes vector X, vector Y, and vector Z. You do need this guy in many machine learning algorithms, including principal component analysis, or PCA. That's why I introduced this to you right now. Okay, the next topic to talk about is called Receiver Operating Characteristic Curve, or ROC curve, and the area under the curve of this ROC. What is that one? So for this, let's go back to that confusion matrix and that example we said about, let's say, banana versus non-banana. So let's say you have some threshold in your machine learning algorithm, and that threshold, based on the visual features, decides whether I should call this a banana or not. Let's say, for example, it's the threshold on the yellow color, right? That if the yellow component is between this much and this much, then we call it a banana. Otherwise, we don't call it a banana, correct? So based on that threshold, which is an important parameter, right? It's one of the hyperparameters of your model. It's one of the model parameters, your machine learning algorithm. Based on that, you do what? You do some predictions. And that gives you some true positive, true negative, false positive, false negative, and so on. And then you look at the recall rate, or true positive rate, this one, which is true positive over true positive plus false negative. So you use some yellow threshold, and based on the performance of your algorithm, you get a true positive rate. Then what? You come and say what? I got a true positive value of, let's say, 0.8. And also, you can calculate a false positive rate. Okay? What is the false positive rate? It is the false positive divided by false positive plus true negative. So it's basically that number divided by the whole row. That is called false positive. While true positive, as you can see, was this number divided by its whole row. Correct? So if I want to write them for you on this graph, the horizontal axis is false positive over false positive plus true negative. And this one was true positive over true positive plus what? As you can see, it is the false negative, right? Which you can also see here. So with the parameter that you have, as I said, let's say the yellow color threshold, you get two numbers for these ratios. And these two numbers in this graph will give you one single point, let's say a point here. By the way, sum of these two numbers is not equal to 1. And also, these two numbers are not equal. The only time the two ratios are equal is when it falls on this line, this dash line, and this dash line means your method only acts as good as random chances, like tossing a coin. It is not really doing any good prediction. Okay, so these two numbers, these two ratios are not equal. Sum of them is also not equal to 1. You can see, for example, here, this point is like somewhere close, less than 0.6, and then the ratio of that is about 0.2. So the hidden parameter, the hidden threshold, when you choose something for it, that gives you 1 point on this graph. Now what would you do? You go and change that yellow threshold. Say, hey, maybe I want to try another threshold, and that yellow threshold maybe gives you this point, right? And then you try another threshold, and then another, and that gives you a bunch of points. And then you connect these points together, and that gives you the ROC curve. So ROC curve is what? Is true positive rate versus false positive rate, where the hidden parameter is, or R is, because each time you only can change one parameter, is the threshold inside, or the parameter inside your model that you can freely change. Good? So now what? Fine. I found this curve. How can I use this curve to talk about the performance of my algorithm, or how do I find whether the threshold I used is a good threshold or not? First of all, what's the ideal case? The ideal case is here, where the true positive rate is 100% and false positive rate is 0. Okay, that's the ideal case. And if you change your threshold and this stays at 1 all the time, that means your threshold literally has no effect on the performance of the algorithm. But if it does, right, so from 1 it drops down a little bit, that means, for example, whatever threshold you chose for that point, that was the best, right? Or whatever threshold, if this graph has a peak, then it shows that threshold is a good threshold, right? Is that the case? No, not necessarily, because remember, here you have a huge positive rate, that's amazing, but you also have a significant what? True false positive rate. So the good points are the points that are high up, but also very much on the left side. If you move to the right side and you move up, that's not necessarily a good thing. You want to be on the left side and up. So this region, I would say, the region like this, that I'm using hatching lines for it, that's a good region of detection, right? If you can tune your parameter to be in that region, that's amazing. But many times, you won't get such amazing performance. You only get something like what I showed you, right? So now how can you talk about the performance of your algorithm? Here you look at the area under the curve. As we said, if your method only does as good as some random guess tossing a coin, then you will get what? You will get this diagonal line. So the area under the curve is going to be 1 times 1 divided by 2, or 1/2. Right? So the worst performance you can have is random performance, where the red curve falls onto the dash line. By the way, the red curve cannot fall below the dash line. It is always at or above the dash line. Okay, so the worst performance is here, this area, which is what? 1/2 area under the curve. The best performance is, as I told you, if you can do perfect positive rates for all different thresholds. So it's a flat line like this. So this is AUC min, and then AUC max. Maximum area under the curve is 1 by 1 rectangle. So depending on where your AUC is, which is between these two numbers, that can tell you for a range of thresholds how good your method is performing. Okay? If you want to set up with one threshold, then there is not so much of discussion. You just tune it to one threshold, and that's a single point here. But if you want to see over a range of thresholds how good your method is doing compared to another method, so you have, let's say, method 1, and there is also some method 2. Which one of them over their hidden parameter, their hidden threshold, does a better job? You say method 2 because the area under the curve of it is better than method 1. It's closer to a perfect case than to a random compared to method 1. So it is, the area under the curve is a measure of performance. The bigger it is, the better your algorithm does perform over a range of thresholds. The next topic we have to cover is called sum of squared errors, mean and root, mean squared errors, and mean absolute errors. And these are some of the things we use a lot in machine learning. So the meaning of them is very clear, but just want to emphasize. So let's say, for example, you are doing a linear regression with a polynomial, let's say a line, and you say that y is a function of x with two hidden parameters a and b. You also have a bunch of observations. So your actual observations, you call them y, and the predictions from your linear model, you call them y hat. Definitely y and y hat are not the same, otherwise you would not have any really regression, right? It's going to be perfect case of curve fitting, right? And it barely happens in real life. It means there is no randomness in your system. So this is what we do in a linear curve fitting or regression least squares curve fitting. So you do subtract the predicted y from the actual y, you get an error. And since these errors could be positive, negative, or 0, and you want to know which set of A and B, which set of parameters will give you the best fit line, the best fitted line, what you do is, in order to find some function that you want to optimize, you want to minimize, you're not just going to simply add these error terms together and say sum of the error. Why? Because the errors positive and negative could cancel each other. So you square, one of the methods is you square these error terms and add them together, and that is called sum of the squared errors. And try to find A and B such that this SSE metric goes to its minimum. That's the way that you do a least squares curve fitting or a regression problem, right? But that's not the only way, that's not the only metric that you use for those optimization problems, sum squared errors. Another way is you divide this summation by the number of points and call it mean squared error. Another way is when you get this mean squared error, you also get the square root of that, and you call it root mean squared error. And another metric is, instead of taking these errors and square them, you take the errors and take absolute value of them and sum it up and then divide it by the number, and you call it mean absolute error, right? That's mean because dividing by n, and absolute error. So SSE, MSE, RMSE, and MAE. These are all different measures of what? Of the error in your prediction, and you try to choose parameters to bring these errors to their minimum. Our next topic is the cost function. And the cost function is basically the function of the unknown parameters of the model that you define. Is typically a function like these error functions, and you try typically to minimize it. Or if it's like another function like entropy that we will see, you try to maximize it. So anyways, it is a function that you try to optimize, and it is a function of your data, and mostly it is a function of your unknown parameters. So let's say if we go back to the problem of fitting a line to a bunch of data, and your unknowns are a and b, then that sum of squared error function that you had, which was a function of the line slope and the y-intercept, you can define it as your cost function. Some in the literature also call it a loss function. And then by taking partial derivatives of that with respect to the individual weights and setting them to 0, and you might need to do a second derivative test also to make sure the stationary point here is actually a minimum or a maximum, you can find what? The solution to those weights. So that is the idea of a cost function or a loss function that you will see a lot in the literature. Now, one of the problems that happen a lot during the basically minimizing a cost function and modeling a system is overfitting. So what is overfitting? Overfitting, which by the way, this topic, regularization and overfitting, is also related to the next category, testing, training data, validation data, generalization curve, and so on. So I would like to cover topics 13 and 14 together. What does that mean? It means, let's say here I have this data, all of these black circles, and I want to fit a polynomial to them. But what order of polynomial is good? You might say, well, I think this could be a line, the underlying function, but with some amount of randomness in the data. Or somebody might say, well, look, I have what? I have 11 data points. So if I choose a polynomial of order 10, then that polynomial order 10 has 11 coefficients, and I can make that 11th order polynomial to pass through each and every one of points. So while for the line, I can only bring down the sum of the squared error down to some value, some minimum. For an 11th or 10th order polynomial, I can make it perfectly 0, which is the minimum amount possible for a squared value. So which one should I go with? A line or a 10th order polynomial? Because it seems like 10th order is amazing, passes through all data. The problem with the 10th order is overfitting. What does that mean? It means you are making the model more complex than what it should be. And how do I know what it is more complex? Well, if instead of a line you pass a higher order polynomial, now this higher order polynomial has a lot of oscillations, as you see in the blue curve. And when it has a lot of oscillations, right, so you used all of these 10, 11 circles, which we call training data. We use all of those to train. And train, when we say, we are mostly talking about neural networks, but here we can also, because when we calculate these derivatives, we are not really training, But if you take it into that context, right? For training here, for these lines, it means calculating derivatives and finding the optimum values. If now I introduce a new point that I have never used, a new point other than these 11 circles, let's say a point right here. At this x of test, I want to know what is the y value. I do have the y value because the test points, not only I have the input for it, I also have the output for it. So if this is the x-axis and this is the y, for this x, let's say I know the point should be somewhere maybe here. Okay, so this is the y desired for that test value, right? This is the point. But if I use now this what? This 10th order polynomial, I have to project this x of t all the way up to here. And so that tells me the y desired for x is this guy here. And look how much that is different or deviated from the actual data. You see why? Because I have this big oscillation. Why do I have the big oscillation? Because the order of polynomial is so high. While if I use the line instead, this would be, instead of this green circle prediction, I would have this green circle, or maybe this green triangle prediction. Look at that from the line. And that gives me this y desired. So which one is closer to the actual one? Definitely the one in the line. Because the line did not make the model very complicated by bringing more and more coefficients. It says, hey, this is a linear relation with some randomness. While here, with the complex model, you say, well, I add more coefficients and try to compensate for all of those randomness, and that makes this poor prediction here for you. Okay, that's overfitting. So if I go ahead and look at what? Look at the error that I can get from my training data, which is the data I used in evaluating or calculating the unknown values, unknown model parameters. If I calculate that error, and it is here called training error, that's sum of squared error, the more I make the model complex, which means what? For example, for the case of polynomial, it means use more coefficients, use a higher order polynomial, right? If I do that, the more I go this way, the smaller I can bring down the error, and ideally, when I have enough coefficients, which is the same as the number of points, I can bring that guy down all the way to 0, right? But if I use a test data that I have never used in my training or in my calculations, what's going to happen? That is this other curve that we call cross-validation error. It's also a sum of squared error, but this is for the data you have never seen. For data you have not used in training. What's going to happen? The problem is if the complexity goes up a little bit, the error might also drop for this unseen data. But once the complexity goes up, which means these oscillations get bigger and bigger, now you have the error going up again, right? So you see the cross-validation error and the training error, they behave differently to higher complexities. One of them always goes down, the other one, which is using surprise new data, keeps going up after a while. And so this new curve here can give me a what? A minimum. And this minimum could be what? The appropriate or the optimal number of coefficients, or the optimal complexity. Correct? So if for this behavior I want to decide what order of polynomial is good, That's what I need to do. I need to reserve and do not use some portion of the data, never use it in the training, and later I bring them and evaluate the performance of the method, the model that I have trained, and see where is it that it curves up. And so that minimal point can tell me, hey, maybe the best order here is a second order or third order, or maybe a line. So this kind of graph that I make is called a generalization curve. This tells me how good, how well I can generalize my model. Can I use my model for all other data that I have never used in my training, or this model is only good for the data I have I have seen? And you might say, well, what's wrong? Why can't I use it for just the data you have seen? Well, there is no learning in that. If your model only works for the data you have used, it's not a real learning. Because instead of all model and everything, you could simply use the lookup table. There is no learning in that. Learning is when you come up with a model that you can apply that model to any data, whether you have seen it or not. That's real learning. Okay, so we always need to generate this generalization curve and find the optimal number of coefficients or the optimum amount of complexity. And as I said, to do that, we split our total data into 3 sets: training set, testing set, and a validation set. Now, what is that? Let me talk about these. Training set is the part that we use to calculate the unknowns. It's the major portion of your data. Test set is what I just told you. Validation is also similar to test. I mean, validation and test you have never seen. What's the difference between them? The validation you use during the training to check the performance of your model and see whether your model's error, cross-validation error, is going up or not. That's why you see here I have used the word validation, right? So you use it during the training to check whether you're doing fine or not, and if you're not, you reduce or change the complexity. Test set is after the modeling is done, after the gains are found and finalized. Now you give it a final test to see how good it is doing. So I emphasize that for you here, that validation data are used during the training. The test is used after the tuning and the parameters are found. That's the difference. So in that aspect, this is kind of like a quiz that you have in a class, and test is like a final exam. Okay? So that's the kind of analogy, if you want. And you might wonder, what percentage of my data should I split to these 3 bins? There is no exact number that I can tell you. One of the common things they mention is like 70% to the training and then 15% on the validation and on the test. Some people use more data toward training. They say 80 or 90%. But this is a common thing that they use in neural networks, 70%, 15-50. Okay, again, not everybody, not every textbook, but this is one of the things I personally remember when my professor of neural networks, Dr. Hagen, who is one of the very famous people in neural networks, he mentioned about the proportions of this data. So hopefully the idea of these 3 categories of data, generalization and overfitting, is clear. Now going back to topic 13, one of the methods that you can use to avoid overfitting is you can bring down the magnitude of some of the coefficients, some of the weights, some of the unknown parameters. What do I mean by that? So you might still have, let's say, instead of a line, you might still have a polynomial, but this time a bigger polynomial, right? But what you can do, let me put some numbers here to make it more tangible. Instead of having a 6th-order polynomial with all 6 numbers being similar to each other in magnitude, you might have something like this. For example, it's 4th-order polynomial, but it is like 1 plus like 2x minus 3x squared, then let's say minus 2x cubed, and then let's say plus 0.01x to the 4, or let's say if we want to go to the 5th-order polynomial, minus 0.006x to the 5. So here you have 6 coefficients, 5th-order polynomial. But if you look, these last 2 have a lot smaller weight compared to the rest of them. And so if you neglect these terms that are 2 or 3 orders of magnitude smaller than everything else, if you can do that, now remember, not always you can do that because these terms are huge. That's why those terms turn out to be small. But if in practice the range of your x is not really changing big time, then if you can neglect these, it is like bringing down the complexity of the model. If you can neglect those almost. So instead of a 5th order, you can practically say, hey, this is a what? This is like a 3rd order polynomial or so. So how do you do that? How can you force some coefficients? Let me add a little bit more zeros to it to make it more meaningful. How can you force some coefficients to be smaller if they are not needed? If I don't need those coefficients really, how can you force their magnitudes to be small? Here, in the addition to your sum of squared error term, which comes from your data and the weights, you add an extra term which is norm of the vector w, and this vector w is the vector of unknowns. So in this case, it is going to be the vector formed by these 6 numbers. Okay, and so when you add that to your optimization function, to your loss function, cost function, not only you're trying to bring down the error, you're also trying to bring down the norm of the weight vector. And so you're encouraging those weights among so many different weight solutions. Those weights come in that not only make the error small, but also they are small themselves. So this extra term that you are adding is called the regularization term. And how would you add it to the sum of squared error? You add it simply, but you add a multiple of that norm of weight to this using what? Using a coefficient, using some constant number which you call Lagrangian multiplier. This constant term lambda here shows the relative importance of this term with respect to this. So if this is more than 1, it means you are adding to the weight of this term. You're saying, hey, this term is a big term. It's important that you have small weights. Even if the error is a little bit bigger than what you got in the previous time I didn't introduce this, right? But this time I want you to go up a little bit in error if you have to, but I definitely want you to make W small. If this is less than 1 means, hey, still the focus is on error, but if you can make W smaller, it would be nice, right? So this W sets up the relative importance. And you're enforcing, but in general, to make the W's with smaller magnitudes, and if they are very small, you can neglect them. So this way, you are kind of enforcing the system to not go so far in the complexity direction. Okay, so this is another way to avoid complexity, is to use an extra regularization term in your loss function. Okay. the final topic here is called the entropy. Entropy is a measure of uncertainty, or you might say surprise, or information content in something that is not certain, in something that has some probability. What does that mean? So if something is certain, certainly happening, the probability is 1, or certainly not happening, probability is 0, we say there is no surprise, there is no information, new information in it. If it's happening with a probability less than 1, then it has some new information in it, or some surprise in it. Let me make it simple by the very simple analogy. And this is like if I tell you, hey, in my town, tomorrow we might get like 40 inches of snowfall, and the probability of that is 60% based on the weather forecast. Then you might be willing to call me tomorrow and say, hey, did you get that huge snowfall? Why did you call? Because I said it might happen with 60% chance. So I didn't say it will definitely happen or will definitely not happen. There was some chance. So when you called me, you're asking for that new information. Hey, did it happen or not? Well, if I said, hey, tomorrow we're going to get that 40-inch snowfall for sure, 100%. Are you going to call me and say, hey, did you get it? Well, you might, but ideally, there is no reason for you to call and ask because I told you it is going to happen. So unless you don't believe me or don't believe the weather forecast, which might happen a lot, you would not call. Or I say, hey, it's not going to happen. We're not going to get even a single inch of snow tomorrow. Tomorrow is predicted to be sunny. Now what? Would you call me and say, hey, did you get 20 inches of snow? No. You know, I told you tomorrow is going to be sunny here. So why should you do that? The probability was 0. So the only surprise or information in there is this field of information technology, which is a very huge field. That's the way that they measure the amount of surprise or information content, and they call it entropy because we have another entropy in thermodynamics. This is a little bit different, although related to that idea, but the mathematical description and everything is quite different than that. So how would you mathematically formulate this entropy? So you say if the probability of the event or the probabilities related to the event is what? It is P, it is shown with the distribution of probabilities of P or Pi, then summation over I of Pi log 2 of Pi with a negative sign is going to be the entropy. And you might say, well, what does that mean? So to show you why this formula has a really useful meaning and explain this curve, let me show you an example. So if I say the rain, right, has a probability of what? Probability of, let's say, 1. What is the opposite of that happening? Not rain. Well, the probability of that is going to be 0. Now, if I say, here I'm talking about binary classes for now, but you can basically expand this, generalize this to more than a binary class. If I say now, what is this term? Could you calculate this term for me for these two different classes? Let's say this is P1, this is what? P2. What would you do? You say it's going to be negative of P1, which is 1, times log 2 of P1, which is 1, minus 0 times log 2 of 0. Well, you know log 2 of 1 is 0, so the first term entirely is 0. What about this? Log of 0, you know in limit it goes to negative infinity. That negative and this negative cancels, so you have 0 times infinity, which is ambiguous. But you know in limit, the limit of p log 2 of p, when p goes to 0, is going to be 0. Hopefully you know that from your calculus, right? You can use the L'Hopital theorem and disambiguate this and show that the limit of this goes to 0, because this term goes to 0 much faster than this term goes to infinity. So the product will definitely go to 0. So the second term is also 0, so the total thing is 0. So you see, if I consider an event with a probability of 1 or 0, and if I consider the binary class of that, the opposite of that, the entropy information for that is going to be what? 0, or it is going to be what? Even if it's 1, it is also going to be what? 0. So you might say, what kind of event gives you the maximum entropy? And that is the event that is 50-50. If an event is 50-50, it has the maximum entropy, and that entropy is 1. Right? Because that's the most uncertain thing to happen, 50-50. You're not giving any side any better chance. So that has the maximum surprise for you. So if this time I say what? I say you're flipping a coin and you have the chance of head, which is 1/2, and you have the chance of tail, which is also what? 1/2. Now what? Now what you need to calculate this time is 2 times negative 1/2 log 2 of 1/2, right? Because you have 2 of this term. And how much is it? Well, you know log 2 of 1/2 is negative 1. And these negatives would cancel out, so we get 1/2 plus 1/2, which is what? 1, as you could see. Correct? So this is the idea of entropy and the formulation of the entropy. And where would you see that? In which machine learning would you see it? In a bunch, but the most common one are the decision trees. In the decision trees that I mentioned in my first video that you use, they are like the 20-question game. In those, you try to go in the directions, you try to ask questions and put the questions where they maximize the total entropy. Okay, so this idea is used in machine learning a lot, or in my next video, I'm gonna stop the video after this because I have already covered 15 topics, but in the beginning of the next video, you'll see me talk about cross entropy, and we also use the idea of entropy over there, but between different types of variables with P and Q probabilities, and you'll see that this is the kind of thing that I can use in like logistic regression. So this idea of entropy is very useful and common in machine learning. So hopefully these 15 topics I have covered in this video so far were useful to you, and I will see you in my next video with the rest of the 15 topics. And hopefully after that we have enough of I would say prerequisite material for the machine learning videos that we'll see in the future. Thank you so much.